Okay, so at this point, we know how to create these word embeddings, and they are very interesting because they expose these very useful properties, and basically they are capturing the semantics. Like, for example, something that you see here in this slide. So in this slide, I'm talking about the problem of synonymy. So it's basically when you have two words with the same meaning, or with a very similar meaning. So if we use word embeddings, what will happen is what you see in, what will hopefully happen is what you see here in this image. So you see that these two, the two vectors for these two words that have very similar semantics, they are very, very close. And now, given this, if I use a model on these word embeddings, it will be much easier for him to understand that these two words, they have a similar meaning. So we can say that word embeddings, they really help with the problem of synonymy. But unfortunately, they don't help at all with the opposite problem. So the opposite problem, which is called polysemy, is when you have one word that now has two meanings. And these meanings depends on the context where we are using the words. And you see the example here that I'm looking at the word book. And on the left, I have this, I read a book. And now the book is this object that I can read. On the right, I have, did you book that room? And now book is this verb, which means to reserve the room. And unfortunately, if I use word2vec, word embeddings in general, what I end up, when I ask the vector for book, I always get the same vector. So you see there is no distinction now, and the model has to do more work to try to understand that actually we are talking about two different semantics here. So how can we solve this? Well, the intuition is that instead of, with word embeddings, we are basically replying to the question, what is the embedding for a given word? Like in this case, give me the embedding for the word book. But if we want to deal with, if we want to consider the context so that we will be able to deal with the problem of polysemy, we should change this question. It should become something like, what is the embedding for the word book, given that the context is, I read a book. And this is indeed what happens with this system called ELMO, where ELMO stands for Embeddings from Language Models. So ELMO is indeed generating these contextualized word embeddings, and is doing that in an unsupervised way. Sorry, in an unsupervised pre-training phase, which is exactly what word2vec or fasttext were doing before. And to do that, ELMO is basing this pre-training phase on this task that is called language model, which is really a key task today in NLP, and actually you will see this task today in the tutorial. So language modeling is the task of modeling the probability of some text. But one application, which is the part that we are really interested in here, is to predict the next word. So we can train a model just to predict the next word. And the idea is that if the model is able to do that, it is hopefully capturing all this syntactical and semantic information that, that hopefully will help our embeddings to really expose the properties that we have seen before in this presentation. So just to give an example of how language modeling works. So we can feed the model the word Alan, and we ask the model what is the next word, and in this case, hopefully will give us the output Turing. Then we can continue to do so. Like we can feed to the model the word Alan Turing, and then the model should give us the word lived, and so on. And then we have Alan Turing lived, and so on. So you can see that the key, one key point is that language modeling is unsupervised. So this, and you can see from this example why. I don't need to label the output, I can just read it from the text. And this is very important because it means that I will be able to in a very cheap way to get a lot of data. I just go maybe on Wikipedia and I download all Wikipedia and I can train all this model over Wikipedia. And language modeling, so here you see it goes left to right, but actually it can also go right to left. So here we are asking the model to predict the previous word. So again, you see that England, we are giving this to the model and this predicting the word in. If I give England and then in, it will predict the word, I think is live, and so on. And this will be actually very interesting because, as we mentioned in the first presentation, sometimes we have bidirectional LSTM or RNN, and if we want to train a language model, we need both these tasks. So let's take a look at how Elmo, what is the model architecture of Elmo. And actually, Elmo is just a n-layer bidirectional LSTM. So Elmo is based on LSTM. And you can see here the idea. So basically, it's kind of having two pieces of the model. You see here this left to right part, and you see here the right to left. So you see that the left to right, I'm maybe feeding Alan Turing, and I'm asking this part of the model to produce the word lived. Here instead I have the right to left. So here I feed in England, and I'm asking the model to produce again the word lived, which is the one just before these two. So the interesting idea is that in doing this, Elmo is hopefully capturing this contextualized representation for the embeddings, which comes from the fact that if you remember how the RNN works, they are creating this internal state which basically is also considering the context around, in particular the context from the past, if we are in this case left to right, and the context from the future, if we are in this case right to left. So it's creating this contextualized view of the current input. And this is all we need. So Elmo indeed is giving us these embeddings, and the way we use Elmo is different from word2vec. Like in word2vec, we were just creating this mapping word to vector, but you see that here Elmo needs all the context. So what we do is we pre-train Elmo, or we download Elmo pre-train, and then we put Elmo between the input and our task. Sorry, the model that we want to use to solve our task. So Elmo goes in the middle, and it will create this contextualized view for the embeddings. And then I can just use the same model I wanted to use before to solve my task. So, okay. Sorry. So results for Elmo, so I will not go into details. So here, basically, the tasks that you see here, some of them are the one that we saw at the beginning of this presentation. Some of them, instead, like the coreference resolution, is just solving the pronouns in a sentence. But in the end, you can see that the interesting part is this last column. In this last column, they are comparing the results of using one model, which they call baseline here. So they use one model to solve these tasks on the left, and then they use Elmo plus the same model to solve the same task. And you can see how now that they increment the results for all the tasks. So you can see that really this idea of having contextualized embedding is helping. And here you see some visualization. So we mentioned that Elmo is creating this contextualized word embedding. So now I can actually plot the words, also considering the context. So you see that now if I have the word bank, and I consider that the context, now I have here on the top left, I have this bank in the context of river bank. In the bottom left, instead, I have all sentences that are related to the bank, the place where I go to put my money. So you see that now they have two different semantics, and in fact, they are far away in this vector space. So this is obviously helping the models, and in fact, we saw how it is improving the results on the task in the slide before.